Hi everybody, welcome to this lecture on binomial distributions. It is a part of a series of short lectures on applied statistics. This lecture will rely on a lecture on Bernoulli and binomial variables. If you're not familiar with that, I have given a link to a brief video in the description that discusses those concepts beneath this video on YouTube. Just attend that. But if you're fresh with that lecture, let's get going. In probability and statistics, we are often interested in what is called a probability distribution. If our random variable can take on many values or have multiple outcomes, then a probability distribution gives the probability of each outcome. So let's consider the Bernoulli process, where a fair coin is tossed 3 times. So x is the random variable that counts the number of heads as the outcome. Then the probability that x equals 0 is 1 over 8. This is because it can only happen when 3 tails appear. The probability that x equals 1 is 3 over 8 because the one head can appear in 3 different orders. We also call 3 different orders as 3 different permutations. Likewise, px equals 2 and px equals 3 are 3 over 8 and 1 over 8 respectively. We can plot these probabilities to see our probability distribution. And note, all the probabilities sum to 1. Note, since x is a discrete variable, because we can count all the different values it can take, the corresponding probability is also discrete. The corresponding probability distribution is also discrete. And if we write all the probability values in this slide together as a mathematical function, then that function is called a probability mass function. For each discrete probability distribution, there's a probability mass function or PMF. The PMF gives the probability of finding a particular outcome. Essentially, the PMF puts all the probabilities that you calculated on the last slide neatly together in the form of a mathematical function. So if small x represents a particular outcome, any outcome, for the random variable that is represented by capital X, then the PMF can be written as on your screens. You can clearly see that this function or the PMF gives probabilities for each unique outcome. For example, if the particular outcome we are interested in is 2 heads, then small x equals 2. And we can easily compute that probability of finding 2 heads equals 3 over 8. When the number of outcomes increases, listing all of them gets hard. For example, if we have 8 hard disks, then there are 256 different ways they can fail. But if we are simply interested in knowing the probability of failure of any number of disks, notice we are not interested in the failure of a particular disk. For example, if x equals 1, then all we care about is that total number of failures equals 1. Therefore, all the 8 sequences that we see are the same for our purposes here. Therefore, we can say that all these sequences represent a single combination. Now, since there are 8 different ways to represent this one combination, the probability of seeing this combination is 8 over 256, where 256 is the total number of unique sequences. Likewise, if x equals 2, we try to list all the sequences. Is the number of sequences again 8? Take a guess. I don't think they are 8. They are more than 8. Trying to list them all will take quite some time. So can't we have just a formula that tells us the number of sequences? Let's see that formula now. Different sequences that correspond to the same combination are computed via this formula here. We call this n choose k or nck. We also use these large brackets to represent n choose k as well, as on your screens. Here n equals the number of Bernoulli trials and k is the same as small x, which is the number of successes. Note, success means what we are counting. So a disk failure is a success here. The formula is n choose k equals n factorial divided by k factorial times n minus k factorial. Notice factorial is a special function marked by the exclamation mark. So n factorial is simply the product of all the numbers starting from n all the way down to 1. And also note 0 factorial is defined as 1. So for x equals 2, we set n equals 8 Bernoulli trials and k equals 2. Therefore, the probability that x equals 2 equals number of different sequences that yield x equals 2 divided by the sample space size. This equals 8 choose 2 divided by 256. Next, we compute 8 choose 2. That is 8 factorial divided by 2 factorials times 6 factorials. And the answer is 28. Hence, the probability of x equals 2 or probability of seeing 2 disk failures equals 28 by 256. So in general, we say that the probability that x equals k equals n choose k divided by the sample space size. Earlier on, we computed the probability of finding exactly one disk failure, and it was 1 divided by 32. I'll leave it for you to verify that this formula can also be used to compute the same probability. So far, we assumed a fair coin. That is, probability of heads equals probability of tails equals 1/2. As a consequence of that, probability of seeing any particular sequence is the same as that of any other sequence, because each sequence appears only once, so probability of every sequence equals 1/8. We can also verify this probability in another way. For example, what is the probability of seeing a head followed by a tail followed by a head? And that equals the product of their individual probabilities, which equals 1/2 times 1/2 times 1/2. And that produces 1/8. Now you can verify yourself that probability of finding another sequence such as head, head, head is also the same. We just substitute the probabilities of getting a head 3 times. Likewise, for the disks, we assume that the probability of disk failure is the same as that of a disk not failing. Since probabilities of all the sequences are identical, we didn't talk about them earlier on while calculating probabilities of the combinations. But what if these probabilities are not the same? Instead, we say the probability of success is P and the probability of failure is Q, and P is not equal to Q. This is quite realistic. Think about it. If your hard disk had a 50% chance of failure over a small period of time, computers won't be reliable at all. So realistically, probability of disk failure is less than the probability of disk not failing. Now, probabilities of each sequence are not identical anymore. Therefore, the probability of finding 8 disk failures equals p to the power of 8. Note, earlier I said p equals probability of success, but here I am setting it to be the probability of disk failure. This is because success and failure are just relative terms in Bernoulli trials. If I'm counting disk failures, then a disk failure is a success for me. Likewise, probability of 8 non-failures equals q to the power of 8. P to the power of 8 is clearly much less than q to the power of 8 because both p and q are fractions. That is, their values vary between 0 and 1. And we know p is less than q, so their higher powers are also similarly different, whereas p to the power of 8 being much less than q to the power of 8. The most important thing to remember, though, is that the probabilities of these two sequences are not identical, and if we want to calculate the probability of combinations that they belong to, then we must consider these probabilities now. Let me show you how. So earlier on, when p equals q, note the general formula, because it is general, applies all the time, even when p equals q. For example, we have seen multiple times now that when n equals 8, k equals 2, and p equals q, that is 1/2, then the probability that x equals 2 is 8 choose 2 divided by 256. Let's compute this probability with the general formula and see if we get the same answer. So let's repeat the general formula here on the screen as we did. And as you can see now, and now substitute n equals 8, k equals 2, and p equals q equals 1/2. So n choose k becomes 8 choose 2, whereas p and q are both 1/2. Clearly, the calculation shows that we get the same result as in the second line of the slide. So really, you just have to remember the general formula if you want to compute probabilities for a binomial distribution. We have seen that to compute the binomial distribution, we have to specify n equals the number of Bernoulli trials and p equals the probability of success. But we do not need to specify q because q equals 1 minus p. And that is because by definition, p and q sum to 1. Once we have specified this, we can find the probability of any k successes. Therefore, n and p are the parameters of the binomial distribution. Therefore, when we write this that appears on your screen, we mean to say that x is a random variable that follows a binomial distribution with n Bernoulli trials and p as the probability of success. Now, because n and p are the parameters of a binomial distribution, changing their values changes the distribution. For example, consider a reference distribution on your screens with n equals 10 and p equals 0.5. Then if we decrease p to 0.4, the distribution shifts to the left. This means smaller number of successes are more common. This makes sense because p equals probability of success and it has just become smaller. But if we bring p back to 0.5 and instead decrease number of trials, that is n to 5, then the higher values simply disappear. That makes sense because with only 5 trials, you cannot see more than 5 successes. Similarly, at n equals 5, if we decrease p to 0.4, the distribution shifts to left again. So essentially, parameters shift a distribution. Some sample code to plot one of these graphs is in the description beneath the video on YouTube. You can play with it and plot more distributions. In probability and statistics, we are often concerned with what value of a random variable we expect to see on average and how much that the value of a variable typically varies. The value that we expect to see on average is called the expected value, and its variability is represented by the variance. The expected value of a random variable x is denoted by e of x, as appears on your screens. In layman's terms, it is the average computed over all the possible values of a random variable, but while also accounting for probabilities of the appearance of each value. I'll show you with an example as to what that means, but formally, the expected value is the average or the arithmetic mean over all the possible outcomes of x weighted by their probabilities. Now, what does that mean? Suppose x is a random variable with only two outcomes, 2 and 4. But you observe that 2 appears more frequently, in fact, with a 2/3 probability, and 4 appears only 1/3 of the time. So the expected value of x equals the probability of 2 times 2 plus probability of 4 times 4, and that equals 2.67. So returning to the binomial distributions, if x is a random variable that is binomially distributed such that the parameters of the binomial distribution are n and p, then the expected value is simply n times p, whereas the variance is n times p times q. Since q simply equals 1 minus p, you can rewrite this formula simply in terms of p as well, as on your screens. Now, if you want to know what is variance, check my last video on descriptive statistics. If you want to look up the proofs of these properties of expected value and variance, you can pick up a good book on probability or check Wikipedia. So here's an example for you to try. If probability of getting a fine day equals 0.4, then what is the expected number of fine days in a week? So let's call the fine day a success, so that the probability of success, that is P, equals 0.4. And likewise, the probability of not getting a success is 0.6, or Q. Then X is a random variable that counts the number of fine days or successes in a week or in 7 days. So X is binomially distributed with n equals 7 and p equals 0.4. We know the formula for expected value of a binomial distribution is n times p. So the answer is just 2.8 days. This means we shall get 2 to 3 fine days, but more often we'll get 3 fine days. We can verify that by checking the probabilities of getting 2 or 3 fine days. So first, we check the probability of getting 3 fine days. You can go through the calculations yourself, but the answer is 0.29. Likewise, the probability of getting 2 fine days equals 0.26. So getting 3 fine days is more likely. You can use the rbinom function in the software called R to randomly generate values of a binomially distributed random variable. Rbinom takes 3 inputs. The small n specifies how many numbers do you want to generate. Size actually means what n means in the binomial distribution literature. That is the number of Bernoulli trials. Since n Bernoulli trials make a Bernoulli process, so size here represents the size of that process. The prob represents the probability of success, or P. So here's a sample attempt. If you set n equals 1, that means you only need to generate one binomially distributed number. We set size equals 10, so the number will vary between 0 and 10, and the probability of success equals 0.5. When I ran this function in R, it generated 4. Maybe you will find a different number. If you just repeat the same in R, you will see a different number, 3 in this case. So why did we get 2 different numbers even though we did not change the way we call the function rbinom? This is because R randomly generates these numbers while trying to mimic a real-world situation. And in the real world, we know the values of random variables change. Now, R uses random number generators to produce different random numbers that follow a given distribution. So next, if you change n to 5, it means you want 5 binomially distributed numbers together. And here they are. If you want to see how a binomial distribution looks like with the given parameters, you must set n to be really high, like 2 to the power of 10, because that almost covers the entire sample space, and you can reliably count which number appears with what frequency. Then you can use R plotting functions to generate the plots like the ones that you saw a couple of slides back. So I'll leave you with an interview question. And the question is, what is the probability that a 7-game series will get into the 7th game or the last game? Note, if somebody gets a decisive advantage like 4-0, 4-1, or 4-2 by the 4th, 5th, or 6th game respectively, then the series does not need to get into the 7th game. So try it out, put your answers in the comments below, and I wish you all the best. So with that, I'll say goodbye, and we'll see you in the next video.